Hello, everyone. Can you hear me? Okay. I'm an undergrad at the Ohio State University, and I've been working with Amber Malpas and Scott Gowdy, bringing astrometric signals to microlensing. So I'd like to start with the basics. In a typical microlensing event, we observe how the light from a distant star temporarily becomes brighter as a foreground object passes in front of it. In an observation, it's basically just a pixel that becomes brighter. And from this brightness over time, we built a light curve. From this data, we try to fit models to figure out what caused the event. This means estimating parameters like how many lenses are there, how far apart are they from each other, what is the mass ratio between them, and what is the source trajectory relatively to the lenses. The separation and mass ratio between the lenses shape the caustics. This is the region where the magnification spike happens. Different caustic structures gives us different light curves. So it is crucial to constrain these parameters as tightly as possible. And as you can see, different combinations of these parameters gives us different shapes. But photometry alone often leaves us with degeneracies. This means that different parameters can give us the same light curves. So some of these examples would be, am I looking at a double source or a binary lens? Or is the second lens inside or outside the Einstein ring? And this is where astrometric microlensing comes in. To show you this, here's a simulation of a binary lens system. So that brightening pixel that I was talking about, in reality, is made up of multiple distorted images created by the lens. In different words, the total brightness comes from these multiple images and not from a single point. And as you can see on the screen, the dots that are moving, these are the images created in the event. So by measuring how the center of light, called the centroid, shifts on the sky during the event, we get a second set of data that can help break these degeneracies. At each time step in the microlensing event, we solve the lens equation to get all the image position, compute their individual magnifications, and take a weighted average of these image positions. That gives us the apparent center of light, and we subtract the original source position to get the shift. And this is what you will see. On my right is just a 2D trajectory, and the centroid looping and wobbling as the event unfolds. But to make this effect clearer, we can project it into a one dimension and see how much wobble there is over time. And one of the degeneracies that I was talking about is that when we look at the light curve of a binary source or a binary lens, they look pretty similar. But when we look at the astrometric data, we can see that the wobble points differently. For a binary source, it points inwards, and for a binary lens, it points outwards. So this is to showcase how strong astrometric data can gives us a lot more stuff from our lensing event. And this is exactly where the Roman Space Telescope becomes crucial. With its planned microlensing survey of the galactic bulge, Roman will achieve astrometric precision of 3 to 10 microarc seconds, allowing us to systematically detect these small centroid shifts. Most of the work has been done as part of a data challenge to help the community prepare for Roman's data set. If any of you are interested in participating or learning more about this data challenge, there's a QR code that you can scan. And most of this effort, I've been integrating astrometric centroid shifts calculations into their simulations outputs. My main contribution has been working on a Python package that can simulate single, double, and triple lens systems. You can see the light curve, centroid shifts, and an animation like you saw before. And this is built on top of widely used microlensing libraries and is designed to help researchers visualize and analyze microlensing events. So now that I hopefully showed how important astrometric can be, or astrometry can be, let's talk about the cool stuff. We can talk about exomoons now. And up to now, most of the work on detecting exomoons through microlensing has focused on the photometric side. In particular, there's a paper by Leibig and Wansgans in 2010 that explores this detectability of exomoons through light curves. My work builds directly on theirs. What I've been adding is the astrometric perspective to it. So they have a general lens arrangement where they've chosen an M dwarf star, because that's typically what you'll find in the galactic bulge. And we have a Saturn-like planet with an Earth mass moon. They choose a wide separation so we can actually see the different caustic shapes between these lenses. So here's the photometric simulation. As you can see to my right, you get to see two caustics. The big one is from the planet star, and the little one is from the moon planet. Now the line, it's our trajectory, and as you can see when we look at the photometric data, if we look at a double lens simulation, we only get two peaks. But when we treat it as a triple simulation, you'll see we get an extra peak. This is showcasing that, in fact, we can see that there's an extra body when we look at photometric data. Unfortunately, this is just a very specific scenario. And this is what the preliminary astrometric simulation looks like. And you can see there's still a big difference between both models. The lines in red, that is the sensitivity of Roman. And so anything that is above or below, Roman will be most likely be able to detect these subtle perturbations. So let's look at a not perfect case. So I'm going to vary now where the trajectory is. The first one was around 1% to the center of the Einstein ring. Now we're twice as far. And as you can see, the light curve starts becoming ambiguous. It starts looking a lot like. So it might be too hard to detect that there's a third body. But when we look at the astrometric signal, there is a huge difference still. So let's double that. Now you can see that the light curve, some people might even say that there's not even a planet there. So it becomes harder to distinguish this. But once again, when we look at the astrometric data, we can see that there's still a huge difference that Roman will be able to pick. Now let's vary the moon position. At the bottom, you'll see that at first the moon was above, now we have it at the bottom. So the caustic changes position. And you'll see that now it's harder to differentiate if there's a third body or not in the light curve. Yet the astrometric data still shows a very distinguishable difference. For future considerations, I do want to emphasize that this is preliminary results. So I would like to explore different parameters. We need to add uncertainties. We need to cross-validate with other triple lens solvers. Unfortunately, there's not too many, so it makes this a little bit harder. We need to take in consideration the ambient blending from other stars near the source. We need to add limb darkening effects and also the moon dynamics. Most of these events take around a month, so we expect the moons to be moving relatively, at least done full trajectory. So that means that the caustic will also move. I do like to acknowledge before I wrap up that this work has been done through other packages, specifically BV microlensing and triple lensing. I'd like to thank their developers for doing this. I'd like to thank my advisors for helping me through this, the Roman team, because they've been very helpful, and of course, the team that brought this conference together. And with this, I leave you with my summary, and I can take any questions.
Great. If we have time for questions.
Hi, Gregory. Really cool. So I'm actually wondering if we'll ever be able to detect multiple events of the same system to do follow-up.
Oh, that is a great question. I would suspect, given that there is the different caustic shapes, I will say that the more bodies there is in the lens, the harder it becomes. For a triple lens system to be able to solve the lens equation, it's already a 10th order polynomial. So to add even more, I believe it's n+1. So it will be quite difficult.
Hi, Jorge Sanchez, ASU. Great talk. You mentioned that you were looking next into adding uncertainties into some of the things you talked about. Can you just briefly mention what some of the uncertainties you think about folding in? What are some of the largest uncertainties you're considering when the next stages of these of your work?
Yeah, unfortunately, I don't have an answer at the top of my head. this is something that I have been looking with my advisor and mostly seeing what is the uncertainties of the precision of Roman, but that's still in development. But I'm more than happy to reach out when I get an answer for that.
Great. Any other questions for a speaker? Good on time.
Yeah.
Great. Oh, with that, let's thank our speaker again.